Get on this here. All right, 8.3, scale diagrams. So chapter 8, as we've already studied in 8.1 and 8.2, we're talking about rates, we're talking about comparisons with dimension comparisons and that sort of thing. We're talking about proportions and equations with fractions and that kind of thing. So 8.3 scale diagrams, this has to do with ratios of models or diagrams versus the size or the dimensions of the real thing. So scale diagrams, you all know about scale diagrams. You've all had to draw a diagram of something that's very large in real life on your paper, or something that's very small in real life, like a cell on your paper. So you've enlarged that, so to draw the diagram and label it and all that. You've all done all that sort of stuff. So let's get into the math of this. The next two sections are the math of scale diagrams. So a scale diagram over here on the right says it's a drawing in which measurements are proportionally reduced, so getting smaller, or enlarged, getting bigger, from actual measurements. A scale diagram is similar to the original. So I think we understand everything that's in this little definition here, okay? Reduced and enlarged, you know what those means. You know what proportional means. I want to talk about similar. This is a similar kind of means kind of the same, right? When you're just talking about in real language, you know, oh, that's a very similar type situation. In math, if two shapes are similar, two diagrams are similar, it means that they have proportional dimensions. They are the same shape, but can be different size. Okay. Now, I say can be, most of the time they will be when we're talking about scaling things up or down, but really, it could be the exact same size. It's just a scale of one, really, you know? It's like, it's the same. But the important part here is two shapes are similar if they are the same shape, which means that the lengths of their dimensions, their linear, their straight dimensions, the lengths could be different, but the angles would be the same to make them the same shape, okay? So think about this. I'm gonna make a triangle right here, okay? Ooh, upside down or right side up? What do you want? Let's do right side up. Okay, so there's a triangle. I'm gonna copy and paste that thing, and I'm gonna make one over here, but I'm going to do this, okay? So these two shapes are similar because they are the exact same shape. They're the same angles. The angles are the same. They don't change when something gets bigger or smaller, but the lengths of the sides will change. What is going on? I don't know why that's flashing on me. Okay, so the lengths of the sides might be different, but the general shape should be the same. If the shape was totally different, that means the angles would be different. So watch this. If I do this, these two shapes are not similar now. They're not similar. Well, you might say, well, they're both triangles. That's similar enough. No. Similar means they have the exact same shape, but just can be different size. And I don't know why I didn't finish writing size there. Different size. Said it, didn't write it. All right, so we understand similar shapes. Now, if we have two similar shapes that are different sizes, let's say this is the original. I'm going to say that this is the original shape, and this is my diagram, okay, or my model. So we're talking about 2D stuff here, two-dimensional models. You think maybe three-dimensional model, but we're talking about 2D stuff here. Easier to draw. So original and diagram. So a scale between two similar shapes is the ratio of a measurement on the diagram, so that's the diagram, to the corresponding distance measured on the actual shape or the original. On the, I'm going to say object represented, that's the original. Okay? So the scale factor here is always on top is the diagram or model, dimension. And remember, dimension is just kind of a length of a part. Diagram dimension divided by, or corresponding to, a ratio of, to the original. dimension. And of course, these have to be the corresponding dimensions. I won't write corresponding, but the corresponding original dimension. So these are the 2 marks that I made here, right? Here's the original, and here is the corresponding diagram dimension. So let's say that this original was 1 whatever, centimeter, meter, whatever. It's about 1 centimeter on my screen. And this one is 2 centimeters, okay? So 1 to 2. Now, the scale factor is going to be the diagram dimension, which is 2 here, divided by the corresponding original diagram dimension, or original dimension. So it's divided by 1. So the scale factor here would be S dot F dot, that's how we can abbreviate scale factor, is 2 over 1, or just plain old 2. The scale factor is 2. So we've basically multiplied this measurement times 2 to get the measurement on the diagram. That makes sense, right? Is it pretty easy? Yeah? Is this pretty clear? Okay. So just remember when you're doing scale factor, the one important thing is the model or the diagram goes on top. Okay? Always on top. And the original is on the bottom. It's a ratio compared to the original. Always compared to the original on the bottom. All right, a couple notes here. Scale is written without units. So notice I don't have centimeters here. The scale factor is just a number because the units should cancel out. They should divide out on top. You should have the same units on top and bottom, therefore they would divide out. So if you don't have these in the same units, then technically that's not a true scale factor. They have to be in the same units. Okay? Now, I don't know if it... okay. It doesn't really mention that anywhere, but dimensions... we should probably write that down. Let's write that down. Dimensions measured need to be in same units to truly get a scale factor. Because if you think about that, if they were in different units, you could say, oh, these 2 similar objects, this dimension is 1 centimeter, this dimension is 1 meter, so the scale factor is 1 divided by 1. No, they're not the same, because they're different units, so 1 is much bigger, right? So you have to have same units in order to get a true gauge of the scale factor. Okay, another note that I'll highlight here, and this will be obvious as you kind of get more practice, but if the model or the scale diagram is smaller than the actual object, opposite of the example that we just did, then the scale will be a number between 0 and 1. So it will be like a decimal between 0 and 1. Okay? Now it won't be 0. It won't be including 0. Okay? Because if you have a length times 0, well then that length is 0. So you can't really have a diagram of something that has dimensions all with 0 length. That's like a point in space that you can't even see. So it's not going to be 0. You're not going to have a scale factor of 0. A scale factor of 1, A scale factor of 1 means that the diagram is the exact same as the original, which is like, kind of what's the point? We don't normally do that. So it's usually, if it's smaller, it's always between 0, it's greater than 0, and less than 1. Okay? So we don't include 0 or 1. If it's smaller, it's going to be between. And conversely, if the model or diagram is larger than the actual object, then the scale factor is larger than 1, as in the example that we just did. Okay? See if I can get the example and those notes on the same page. So this one is bigger, scale factor is larger than 1. You say that? Okay, pause for any questions or clarifications. Any questions or clarifications from the studio audience here? You guys are all just so smart. You're tracking with me. I haven't made any mistakes up there yet that you can see? No? Okay, that's always good. All right, let's do an example then. Here's an example of someone's science project here. We've got, like I mentioned before in the intro, we've got a model of the cell. Oh, wow. Right on. I remember doing that in elementary school too. The model of the cell. Okay, so this example from the textbook, it says the diameter of the animal cell that is represented by this scale diagram is actually 0.25 millimeters. So the diameter, the actual diameter, all the way across the middle of the diagram here, is 0.25 millimeters. What scale factor was used to draw this scale diagram? Okay. Well, the nice thing about this is that we have a formula for scale factor, right? That is diagram measurement over original measurement, and they have to be in the same units. So right now I'm seeing, first of all, that I have a unit in millimeters and a unit in centimeters. That's a bit of a problem. To do scale factor, they have to be in the same units. So what do you think? Do you want to move, which one do you, what unit should we settle on here? Okay, some say centimeters, some say millimeters. It doesn't really matter, but it's usually easier to multiply a number than to divide, but it's not a big deal. It's like a factor of 10, right? So I heard centimeters. So if we're going to, well, let's do millimeters, because the smaller one is usually the better bet, because then we make them bigger. So 3.5 centimeters is times 10, that's 35 millimeters, right? Okay, because centimeters and millimeters, they're only one step apart on the metric staircase there, if you remember. So this is 35 millimeters. Okay, so scale factor always has diagram on top, so that's going to be 35 millimeters on top. You can use your units. If you know that they're the same, you don't have to write them down, because they're going to cancel each other out. But over here is divided by 0.25 millimeters. Those units cancel out. And the scale factor, when you do that on your calculator, you can actually do this one in your head fairly easily. When you divide by 0.25, that's the same as multiplying by what? Anyone know? Multiplying by 4. Because 0.25 is 1 over 4. So when you divide by 1 over 4, you flip and multiply. So that means you multiply by 4 over 1. So what's 30 times 4? That's 120. What's 5 times 4? Is another 20. So is this 140? 140, is that what you got? Okay, so that's the scale factor. So this is 140 times as big, times as large. Doesn't look like large. L-A-R-G-E. Okay, got it? What's the scale factor? Okay, scale factor is actually 140. That's what the question asks. And there's the explanation. All right. Look good. Any problems with that? Any clarifying questions you want to ask there? We're good so far? Okay. Got a couple other notes I want to talk to you about. What happens if you are given two similar objects, and you're given their dimensions? Is it fairly easy to determine the scale factor then? Well, it is, yeah. So what's the scale factor here? Well, the scale factor is going to be our diagram or model measurement divided by original. Now it has to be the corresponding one. So we look at these two shapes, and yes, these are similar. They're the same shape, but one is just bigger than the other. So the diagram appears to be larger than the original. And yes, this one's pretty easy because this length right here has a corresponding length over here, and we're actually given all those measurements. So the scale factor here for this is going to be this measurement on the diagram, 8.8. They're both in the same units, so that's good. Divided by the corresponding part measurement, which is 4. And so the scale factor here is, what's that, 2.2? Yeah. 2.2. Awesome. Now what you want to be careful with is this, guys. Oh gosh, I didn't mean to do that. Let me see. What you want to be careful with is this. If you're given this as 10.2 down here, and this as 8.8 up here, you're going to have to make sure that you pick the two corresponding parts. So you can't pick this side length and this side length to compare, can you? Because they are not corresponding parts. So it would be like two people if you have a right arm and a right arm. Those are corresponding parts, right? So two diagrams, the top in this orientation and the top in the same orientation. Because you're going to have diagrams that are like on the side or flipped all the way around, and you have to kind of like identify which part is corresponding. It's going to get a little trickier that way, right? Like, for example, if I did the two triangles, okay, like this, and then I had another one, but oh, can I do it now? Oh, darn, I don't think I can. Okay, hang on. But if I had another one that was like oriented the other way, right? And let's say these were similar, try and get them the same shape. Get rid of this one. So now you're gonna have to be real careful, right? Like X and Y, are those corresponding? You kind of got to switch it around in your head. If you switch this around in your head and they were both oriented the same way, then the Y would be over here. So this X, now, if this is isosceles, then fine, you can use it. But if it's not, like if somehow these angles were different, well, this angle would go with which one? Which one of these? Okay. So then this would be your corresponding one here, the W and the X, right? Because 1, 2, 3. 1, 2, 3. It's the side that connects the angle number 2 and angle number 3, angle number 2, angle number 3. So W and X would be the corresponding parts. So you have to be aware of that one. That make sense? Is that okay? Yeah? All right. Okay. Some of you are nodding. I can't tell if you're falling asleep or if you're nodding yes. All right. So 2 more things I want to tell you before I'll do some homework with you. Get started on your homework with you. So this one here, just a note on enlargements. You're going to see percentage. You're going to see percent enlargements or reductions. So just a note on that. The actual scale factor is the decimal form of the percent. Okay, so if something is 250% larger, it's not 250 times larger. It's not. It's actually 2.5 times as large. So the scale factor is the decimal form of the percent. And that sometimes students that are not paying attention see the 250% and go, oh, times 250. No problem. Not so fast. Times the decimal form. Okay? Because think about it, if something is 100% as large, 100% as large means that it's the same. Okay? That means it's the same. It's 1. A scale factor of 1. It's 100% of the original. Okay, that means it's the exact same as the original. If something is a percent that's less than 100, like 33%, oh gosh, that is 0.3. I don't know why I hit, I guess. Actually, I think I meant both of these to be 0, so let me just change it to 0. If something is 30%, it is the decimal form 0.3 times large. Okay, why did I do that? Because I have these 3 diagrams. Look at this. Let's say that this is my original right here in the middle. Okay, and that is a 1 right there. So obviously this is going to be an enlargement over here, and this one's going to be a reduction. So look at this little guy right here. Let's see if I can grab him. Click. Okay. You ready? Actually, I'm going to zoom in a little bit. Okay, I'm going to bring this guy over. Okay. Look at this. 1, 2, 3. Approximately 3. Okay, maybe a little bit more, but it's approximately 3.3. So this one is 0.3, let's say. Okay, it's a third. And we'll say that this side. Okay, so that's 30% of this one. Now be careful with the area. We're not talking about the area inside, we're talking about dimensions. So this one, the big one over here, okay, if I move this over, this is going to be 1, 2 and a half. See, that side is about 2.5. So that's where you get your 250%. Next section, we will compare areas of figures, but right now we're just talking about dimensions, because it's actually slightly different rules for areas and for volumes of 3-dimensional objects, okay? So this is just for dimensions. Hey, everything clicking so far, yeah? Sound good? 100%. Look at this. 100%. I don't want 100%. What do I want? I want 75%. Oh. Can you see that? No? Okay. Yeah. All right. Now, the last thing I'll just kind of talk to you a little bit about here. To create a scale diagram, sometimes you're going to have to think in the reverse process, or you have to pick out a scale factor to make the two ratios, the two numbers in the ratio, reasonable. So let's say if you have to create a scale diagram, you might have to choose an appropriate scale. To do this, determine one dimension of the diagram model and calculate the scale for all the other ones. And here's the example I'd like to present to you. The Empire State Building in New York, those of you that were in the Annie production, what other town has the Empire State and a mayor 5'2"? The Empire State Building is 381 meters tall, very tall. I have been on top of the Empire State Building, I believe twice. It's an amazing view of Manhattan. I love it. It was very, very cool. If you wanted to draw a diagram of this building that fit on a regular sheet of paper, what scale would you use? There's a question for you. Now, a regular piece of paper is 8.5 inches by 11 inches. 8.5 by 11. That's the size of a regular piece of paper. So I'm going to put this on here somewhere. I need to know what the scale is. Not a good idea probably just to guess and check. Like, oh, what about 0.5? Oh yeah, 0.5. That's right, 100 and, 60 some meters. Yeah, is this 160 meters? No. So it's not 0.5. We got to go quite a bit lower than that, right? So what you want to do is probably figure out what dimension you want to make the height of the Empire State Building on your paper. And so a regular paper is about 11 inches tall. So this is in meters, so we probably should think about a similar unit. And I'm thinking we should probably use centimeters. This is easy to go to centimeters, okay? So let's go to centimeters there. So we've got 381 meters. In centimeters, what do we do to get centimeters? Multiply by? 100, thank you. So put 2 zeros on there. And that's going to be now centimeters, because there's 100 centimeters for every 1 meter, so multiply by 100. Awesome. Okay, so that's my original. See, scale, see what I'm doing here? Scale factor. So what should be, how many centimeters do I want to make the height of the Empire State Building? Okay. Here's the Empire State Building. Okay. So 11 inches is the total. Let's go under that, right? We're going to have to go like maybe 9 inches. Maybe how many centimeters would, let's say 9. Let's say 9 inches. Okay, 2 centimeters. How many? What are we going to do there? What's the conversion rate? Do we know a number? Centimeters and inches? What's the conversion there? Do you know how many centimeters per inch? No? We don't know this? No, not. Oh. You guys don't know this, really? Okay, all right, that's fine. Didn't we do this in like grade 10? Yeah. You guys are in grade 10. We did this last semester. Yeah. See, you should study for finals. It was actually more than a semester ago. Yeah, it was at the beginning of the year. So when you learn stuff in math, like more than a semester ago, you don't actually learn it. You just memorize it and regurgitate it.
Conversions to remember.
There's so many conversions from. Yes, life is hard for you. That is true. Okay, anyone? Come on. Okay, 2.54. Thank you.
Oh, I remember that.
2.5. Oh, now we remember. Okay. Okay. All right. I'll give you a hard time. You guys forget stuff. I get it. I forget stuff too. I can't remember what I've forgotten, but I've probably forgotten something. That was a bit of a joke, but. You get that or no?
Yeah, you forget.
I forget what I've forgotten. That's okay. Anyways, that's a bad teacher joke. Where the heck was I? Okay. So how many centimeters is 9 inches then? I'm going to go 9 inches times 2.54 over 1. right? And the inches are going to cancel off. So 9 times 2.54, what do you get there?
22.86.
22.86. Is that confirmed with other mathematicians in the room? You guys are mathematicians, at least during this period of the day you are. That's all you're doing is math, right? Okay, so we're getting close now. We've got our diagram, our proposed diagram height divided by the original height. And what do we get there? Is it going to be a big number or a small number? It's going to be pretty small. You got 22 out of like 38,000, so that's not a very good mark on the test. That's a pretty low percentage there, isn't it? 22 out of 38,000. But yeah, of course the scale is going to be quite small because our diagram is quite a bit smaller. So let's see, do I have this yet? Okay. 22 on. Clear. 22.86 divided by 38100. Yes. Whoa, what does that mean? 6e negative 4, what does that mean? 6 times 10 to the negative 4. That's scientific notation, my friends. Which means that from this proposed decimal place, we got to go to the left 4 times to get the actual decimal, which is 3 zeros and a 6. So that's a really small number. Okay. Scale factor, pretty small. Okay, you good to go?
Yeah.
Everybody get that? How many centimeters in an inch?
2.54.
Very good, 2.54. No, you're not going to forget that now. Okay, I'm going to end this video now on the lesson, but I will... Yeah, I'm recording.
That was easy.
That was easy. What else do I have up here? Soup's up!
Cody!
I feel like I'm in a diner, a 50s diner. Grilled cheese sandwich! Table 4!
Did you say soup's up or surf's up?
Soup. I said soup's up. Surf's up?
I don't know, that's what I heard.
No, soup. Like the soup is up, it's ready to be taken. That's what they used to do back in the old days. They put the cook's food ready, ding the bell. Turn around.
Dad.
Oh, go get the food. Who do you want a special shout out to? Just wait. When I end the video, which is going to be any second now, you guys can do a shout out.
No, it has to be special one from you.
To who?
Chicken Joe from Surf's Up. And say Cody.
Special shout out to Surfer Joe?
No, Chicken Joe.
To Chicken Joe? From Surf's Up.
And say Cody.
Cody! Normally I don't just do whatever students tell me to do, so I hope I haven't done anything bad. Did I do anything inappropriate there?
No.
Yeah, right. Okay. All right, what do you have to say as a class at the end of this video to all of those the thousands and thousands of students that are listening right now? What do you have to say?
Act your age, not your shoe size.
Act your age, not your shoe size. Okay, good. Unless you're 5, you can be more mature. But I guess what's your shoe size there? Oh, no. If you're small, your shoe sizes are actually larger.
No, because
Because the actual youth sizes don't start until you're older.
But then don't have
But listen, when you're 3, you could be size 10.
But don't be overconfident, no? Like don't act
Okay,
like you're cooler.
for high school people, act your age, not your shoe size. And for those of you with big feet, you need to have loftier expectations for yourself. Does anyone have a shoe size that's greater than their age? What are you guys, 16?
Reynolds
13.
No, Reynolds 13.
There's no way.
Okay, fine.
It says 12.